I'm going to show you how to manage massively parallelized LLM API calls using Prefect. We're going to use Prefect's Concurrency API to make sure that we can distribute thousands of LLM calls without tripping our rate limits or breaking our token budget. Let's dive in. So the project that we're going to work on today as an example is a classic one that everybody's come across. How do I know if I'm a good fit for a particular job? So what we're going to do is we're going to go over several job boards, and we're going to build a pipeline that goes and scrapes all the jobs from those job boards, compares them to my resume, and then passes it off to an LLM to ask whether or not I'm a good fit. So why is this a hard problem? It's a hard problem because if you go look at any one of these job boards, you're going to see thousands and thousands and thousands of jobs. This is hard for a human to do, but it's also kind of hard for a machine to do too because of problems in concurrency. Concurrency is the problem of how do you manage massively parallelized calls to a centralized resource? When we think about something like OpenAI, they serve hundreds of thousands of developers. In order to protect the integrity of their system for everybody, they have to make sure that any individual who's accessing their API does so respectfully. So they enforce a request per minute, something like a speed limit, but also a token budget to make sure that nobody's requesting too many resources from their GPUs at the same time. So they enforce these two rules against any organization that's making requests into OpenAI. Now, why is this a problem? If I go to a place like Stripe, and let's say I'm just doing this with raw Python, I might go to the API for their job board, and I'm going to see that I've got, hundreds of jobs that I can process. And so what I'm going to do is I'm going to take every single job, and then I'm going to throw them all at OpenAI at the same time. But if Stripe adds 200 jobs tomorrow and 200 jobs the day after that, now we have a real resiliency risk to where we could be sending hundreds of calls to OpenAI, tripping their rate limits. Also, these job descriptions can get pretty long. Given that we're also sending my resume along with every single request, you can now get to a point where one day's run could consume your entire token budget. And that's just for one developer. At an organization, it's rare that I'm the only developer who's trying to make requests against an LLM provider. So I'm often only given a fraction of my company's token budget. And so I have to make sure that I respect those constraints, not just for the jobs that I'm running, but so that the rate limit or token budget errors aren't felt by my team members who I may not even work with on a day-to-day basis. Let's dive in to see exactly how that works. Okay, so let's take a look at a standard project. So I'm going to first import my usual libraries. We're going to do this all async because it's a lot of I/O operations. So I don't want these I/O operations to block. I'm going to import OpenAI. I'm going to use Pydantic as a way of getting structured outputs out of my LLM calls to make sure that I can coerce the responses from your normal ChatGPT slop answer into something that's pretty definitive for me to work with. And then I'm going to load our API key in from our environment variables so that I don't have to expose them during this talk. So for this, this should be pretty straightforward if you've written an LLM pipeline before. I'm going to initialize the client. It's reading its API key from the environment. I'm going to have a pretty simple resume here. You can imagine we could go really hard on this. We could process the actual text file. I'm just going to say, I'm a PM with 8 years of experience across a bunch of different stuff. And I'm going to have the slugs of the job boards, both Stripe and Flatiron Health. But of course, for every job board that we want to do this for, we could just add them here to our slugs. So the type of structure I'm going to be coercing out of every single job description is pretty simple. It's trying to figure out, am I actually a good fit or not? Any question that I wanted to ask of this, I could say requires management experience or something like this. And any field that I put on here with the type annotation is going to help me extract this information from the job description. And so you could go really, really hard on this. You could say it's a fit. I want to tell you why it's a fit. I can go into the requirements, the things that stood out. Anything that I want to mine the actual metadata out of, I can just specify here is in my schema. But I'm not going to have this too long. It consumes tokens in its own right, and I just want to make sure that at the end of the day, I'm getting the answer I want. Is this actually a good fit or not? Okay, so now I've got one function, which is like my transform function here. This is not doing anything particularly fancy. I'm using the beta parse function from OpenAI for structured outputs so that, I can call out the GPT-4o mini and I can pass my resume, I can pass this data, and I can specify that the response format should actually be this job. This is not a talk that's like optimized for prompt engineering. If I was building this in production, you could imagine that like my prompts would be a lot richer. I would be providing a lot more instructions here. But this is really like when we think about just a bare bones pipeline, just trying to give some of the scaffolding for this. And of course, this is really just going to return the parsed message. So anything that comes out of here is going to be a job. And all I have to do is pass in some sort of job description data into this function. So this thing really takes on the role of turning my job description into an instance of job. And so now let's see what's going on with this load function. So I start off with an empty list. And then what I'm going to do is with an HTTPX client, over every single slug that I get, I am going to go scrape the Greenhouse API for that long list of jobs that we just got done talking about. Now I'm going to get the JSON representation of that long list of jobs. I'm going to pull out the actual list of jobs. And then, this is what I'm going to do is I'm going to create a coroutine out of all of these, and then I'm going to await all of them gathered together. The reason, of course, why I'm doing this is like when you're doing a lot of I/O, like in and out, and you're calling out to an external API, you don't want these operations to work synchronously and block each other. And so here is really kind of like best practice code if I was trying to build this in just almost like pure Python without a lot of external dependencies. And of course, just one tricky thing here is, I'm only taking the first 3 jobs from each. This is because if I don't do this, this thing crashes right out of the box because I quickly exceed my rate limit. And so, here I can go in and I can go and run this file. I'm going to do it with UV. My file is called hello.py. And when I hit run, what it's going to do is it's going to go to both those job boards. It's going to pull out the top 3 jobs from each one, and it's going to return whether or not it thinks that it's actually a fit or not. Of course, I'm just getting false on a bunch of stuff. I guess I'm not particularly qualified for anything. But I could say, reasoning, if I really wanted to get something pretty good out of this. Now, if I run this again, I should get some reasoning out of this. And let's see what I get. This is going to be a little bit longer because I'm giving it like this free form text response. And so these could actually be pretty long or deductive. Now I'm going to start getting like, hey, it requires significant experience in oncology. The ideal candidate should have a background as an RN, and the candidate's background as a product manager and this don't quite align with it. So it's actually, it's coercing it in the right way. So I'm going to get rid of this. Now, if I want to get rid of this, I'll show you what happens. The second that I run this, what happens, it hangs forever. It hangs forever. I have no observability into what's going on here. It's just this giant black box and I'm sitting here waiting whether or not something crashed or not. And so this is like the first place that I would bring in a tool like Prefect is to just understand what the heck is going on as I try and execute this. So I'm going to cancel this. And let me go ahead and bring in Prefect. So I'm going to say from Prefect, import flow and task. And what I'm going to do is I really, I want to observe every single time I transform this data. And then what I'm also going to do is I'm going to turn this entire thing into a flow. And so now let me go ahead and add that constraint back in. And let's see what life looks like when we come back to this. So now I immediately get this observability. I know exactly that, I'm kicking off this load job. I'm doing the top 3 from each one of these 3 pieces, or from these 2 pieces. So I get 6 tasks that come out of this. And then I even get a handy little UI that I can go check this out. So if I go check this out, I'll see that indeed I processed each one of these individually, and then my flow completed. So I can see exactly how many of these things happen at the same time. Now, of course, if I go and I take off this constraint, I don't know, let's say go do 20 or something like this, and I run it again, now let's see what happens. Now I should be able to see this happening live, where I'm going to be able to see every single new one come along and actually go do that transformation for me. So now I'm not writing the data anywhere right now. I'm just trying to make sure that everything is happening as I expect it to. Now, of course, this is me throwing, 20, so times 2 is I'm throwing 40 requests at the API. This is still within like the normal realm of what this API would expect. So that's actually not too big of a deal. But of course, the second that we start getting to hundreds and hundreds of requests is when we're going to get a problem. And notice that this is happening pretty eagerly, right? It's like any single time that I've got like basically a free thread to go take this on, I'm actually going and making this request. So a lot of these things are pretty just staggered, like come one, come all to making this request. And and so what I really want to do is I want to be able to take off this kind of shallow constraint here. I want to be able to make as many requests as I want. But of course, I have to respect these both token and rate limits. So what I can do here in Prefect Cloud is I can go over here to concurrency. Now, when I open up concurrency, I'm going to have some pre-made concurrency limits for this demo. But if I were to go in, it's going to give me a chance of adding a concurrency limit. Of course, I can give it a name so I can identify it in code. And then I have to give it a concurrency limit. Now, a concurrency limit is really like how many things are allowed to operate at the same time. And I can give it a slot decay per second, which basically says, as a function of time, how many of these concurrency slots should I return back to the pool of unused slots? So what you don't want to have happen is, you don't want to just like go ahead and take if I'm trying to respect a rate limit request, I may go take a slot. And then as time passes, I want to basically independently go and return that slot back so that something else can go and take it. But if I'm working with something like token limits, I want to make sure that like absolutely nothing is returned back to the pool because I'm really trying to manage those slots very carefully. So here, when I think about my OpenAI rate limit, I'm going to give it basically 2 slots, and I'm going to give it a slot decay per second. Actually, I'm going to have 1 slot here. Now, the reason I do a slot decay per second is I'm trying to make no more than like 10 requests per minute. This is just like for the purposes of this demo. But of course, if we really want to respect like OpenAI's prescribed thing, it depends on your plan type. So I'm just going to go ahead and set the constraint of I don't want to make more than 10 requests to OpenAI per minute. And then of course, I've got a token budget that just for this pipeline I want to respect. I may have other pipelines that I need to run in parallel, but I want to carve out 81,000 tokens just for this pipeline. And so let's try and enforce this actual rate limit request. So what I can do here is from Prefect dot concurrency dot asyncio, I can import rate limit. Now what I can do is I can now await this rate limit. And what this is going to do is it's basically going to block this request as long as I don't have a free spot. So now if I go ahead and I run this exact same thing in parallel, or I run this exact same thing again, what we're going to see is we're going to see that all of these started in parallel, and yet we're actually going to block each one of these so it doesn't actually make a request. So these all look like they started at the same time, and yet now you're seeing that these things aren't actually completing for some regimented amount of time. And so what this is guaranteeing is this guarantees that, this thing right here is almost like blocking and tackling for the rest of the function to sort of make sure that this isn't all executing at the same time. And so what this is doing is this is enforcing this is actually enforcing the rate limit on our behalf so that we don't have to worry about DDoSing this entire process. And so this is making the execution take a lot longer because it's actually respecting that rate limit. So that's managing rate limits. But I also want to manage the token limit as well. So from prefect.concurrency.asyncio, I can also import concurrency. So now what this gives me is this actually gives me a context manager that I can actually use to block on token budgets as well. So I can say, async with concurrency. And let's remember what the name of this token was called. If I go back to concurrency, this is called just simply tokens. What a great name. What I can do is I can say I'm going to take a lock on 16,384 tokens, because I know that's exactly what the context limit is for this, for GPT-04 Mini. And then, of course, in max tokens, I'll also spell out that it can take no more than 16,384. And so what this does is, this basically enforces that I have to respect the OpenAI rate limit. And then this thing enforces that, I'm going to start off with this budget of 81,920. And then what I'm going to do is I'm basically going to say anytime that I go kick off this request, I'm going to steal 16,384 tokens from the budget, and then I'm going to return it back when it's done. And so now, I think this one from before is still running. I can go here and I can cancel it. This should now be in a crash state. I went in and canceled it. But now I can go ahead and run this again. So let's see what happens when I actually kick this off. Now what I can do is I can go and I can go open this in the UI. And now what I'm going to see is I'm going to see this process still staggered as it was before. These jobs, they launched concurrently, but I still have my rate limiter, which is making sure that I'm not actually making my actual request to OpenAI until my speed limit has been respected. So you're seeing all of these things sort of stagger out correctly. But then also what's going on in the background is it's staggering it in a way so that I don't actually trip any of my token budget as well. It's making sure that every single time that I enter into one of these requests, that it's basically taking 16,000 odd tokens out of my budget and declaring to every single other request that it's not allowed to start its request unless it has 16,000 odd tokens that it's allowed to use for its own task. And so in doing so, by combining the rate limit primitive with the concurrency API, we really have a way of enforcing not just the API rate limit, but also making sure that we're not DDoSing our actual token budget. So that's a little bit about how you can use Prefect's concurrency API in order to control massively parallelized LLM API calls. You can make sure that you respect the rate limits or the speed limits of the API, along with token budgets as well, so that you can process millions of documents in parallel without tripping up your token budget or tripping up your rate limits. This is really helpful for when you need to build pipelines, not only that are parallelized themselves, but parallelized over different functions, so that one pipeline can be given one token budget, another pipeline can be given another, and then when you run them in parallel, you never have to worry about them actually butting into each other. Or in organizations, when you want to have one team have a lock on a certain number of tokens and then not necessarily share that with another team, maybe folks are on the consumer side versus folks that are doing a bit more like behind the scenes ETL pipelines. All right, so hopefully you've learned a little bit about how you can use Prefect's concurrency API to add rate limits and token budgets to massively parallelized API calls. Thanks so much.